Welcome to the examples video. We're going to go through 8 examples. So if you need to hop to a particular one, you just go to a description and do lah. First one is on page 16, MJ15 P11. Look at this pattern. The pattern is in the diagram. Maxima and minima. Ooh, interesting. Okay, what can cause this pattern? Coherence, diffraction, interference. So firstly, you see the shape, right? Like this spreading out. It's diffraction. Yes, so there is diffraction involved here. But is it diffraction only or diffraction and interference? This one you must look carefully. You see these dots? They already give to you minima, maxima. So there's interference occurring. So diffraction and interference. Why is there diffraction occurring? Because if you're going through a gap, you will still have all these, what we call wavelets spreading out. Okay. So even though if it's, let's say, a single gap, you still have interference occur because of all these wavelets here. They have many, many small waves. And they all interfere each other. That's why you get this dotted maxima, minima pattern happening here. So if I draw a line through all the maxima, it's kind of hard to draw through the middle. Okay, that will be one of your orders lah. I don't know which order is it. Okay, n equals to something. If you draw everything, then you get all your n equals to 1, 2, 3, 4, 5 line. Okay, the zero order will be the one dead center. See if I can draw this. Oh man, it's off center. Okay, I'll try to fix it. But I can't fix it. Oh, I can fix it. So that will be your zero order ray, which is all the wavefronts constructive along this line. That's your n equals 0. Okay, so remember that. This diffraction and interference. Second question. Look at this beautiful picture. Let's see. So this one is on page 20. I forgot to write. 2020. You have two thick barriers, some water passing through around an obstacle and through a gap. Which statement is correct? Ooh. Okay, diagram both illustrate diffraction. Sounds correct. Diagram is interference. No, interference are usually your fringes. You want to see the fringes. There's no fringes. It's just wave fronts. Interference, nope. Diffraction. I mean, Y is in diffraction. X is also diffraction, so no. Only diagram Y? Nah. So both will show diffraction. So you see the first one, as long as you have an obstacle around a gap, you see your wave is partially obstructed by this obstacle, it will spread out. Okay, it will move around the obstacle very nicely. And if you have obstacle, and it's one slightly slit, yes, you still go through and will spread out lah. That's the diffraction part of it. So you see the curved wave fronts all spreading out. That's for this one. To look at diagrams. This one is an interesting one, page 21. Monochromatic plane wave, speed c, wavelength lambda is directed at a small aperture. What is an aperture? Aperture just means how big is the hole. Okay, so here if it's a slit, then if you have a slide, the slit will look like that. But you can also think of it in terms of circle lah, like this radius. Okay, the wave can come through the circle. Here the wave can come through the slit. Many different ways lah. Aperture is also what we call in camera. Okay, how big is the hole, the lens? How much light is it letting in? Okay, anyway, we have successive wave fronts. So all these lines are your wave fronts. Usually we call them crests lah. After what time will this wave GH reach point P? So you want to think of it this way. This G is a wave front that is traveling, progressive wave, remember? So think of this thing as moving. How to make this move? Moving. And eventually it will reach the slit and then it will spread out and go to P. But how long will it take? That is the question. What equation that has speed? We're moving at a constant speed c, right? So you can think of it this way. Our good old speed is distance over time. This good old thing, remember how to do? Okay, the speed of the wave, electromagnetic wave. How we know electromagnetic? Then they told us C, speed of light. Or monochromatic, single light. Light means speed of light already. Distance over time. Now the distance, how far did this wave travel? Good question. You want to think of it this way. Here to here is one wavelength. If you're wondering why, I draw for you. Okay, imagine this is the wave. This is your wavefront. We'll say the wavefront is the crest. GH. Then the next wavefront is here, the next wavefront is here. So between here and here, that is one full lambda already. Here and here, another full cycle. Okay, so this is how you draw the wavefront now, like that, like that, like that. So that means there's one lambda, another lambda, and another lambda before it reaches P. So it will travel a distance of 3 lambda, therefore you say 3 lambda. So let's see, where got answer anywhere? 3 lambda over T. No, they want T. Oops, forgot. So T equals to 3 lambda over C. That is this one. So remember, waves are traveling at what speed? For light, speed of light. Now we come to structure question 2, page 28. Lots of more writings now. Describe the diffraction of monochromatic light as it passes through a diffraction grating. Describe, you can draw lah. You say, the wave go here, then it spread out. But you need to describe it for 2 marks. So the full way you can say it is that your wave passes through slits. Oh, I only draw one slit in the diagram on the right. But you can say slits or gaps because diffraction grating got many slits. Okay, so the wave passes through the slits and gaps in the grating, depending on your D, how many gaps you have, and spread out into a geometric shadow. This is what we call a geometric shadow. And spread out into geometric shadow. Very fancy word, right? You can call it your band if you ever start a band. Okay, there's many wavelets interfering. So sometimes actually the best way to draw is like the picture just now. You do dotted. Then you also show the interference happening there. Okay, 2 marks here. One comes from wave will pass through the slit in the grating and then spread out into geometric shadow. So that's your A1. This is the one you want to say. Whenever I ask you to describe diffraction, think about this. White light incident on diffraction grating. Zip, 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 zip. Okay. Diffraction pattern form has white light, 0 order. Ooh, white light there. And color spectra in the other orders. So somehow, in the first order, you see white light. In the other orders, then you see other colors. So why is that? You should remember, white light, this white light here coming in has many wavelengths inside there. White light is what? Red, orange, yellow, blue, green, all combined. But then only when it comes to 0 order, you will still see white light right here. But the other orders, different already. Okay, so describe how you can explain white light at 0. Why is it white here? And the rest all got color. The rainbow come out, remember? So you want to say each wavelength, I'm going to shortcut and just use a symbol. Each wavelength in your white light travels the same path difference. Travels the same path, or you say 0 path difference. And therefore, all your wavelengths add up together to become your resultant displacement. And this resultant displacement is all constructive. So I just make a note here, constructive interference. So it means if your white light come through here, got all colors inside, right? And then it's just straight so the 0 order is always constructive, always maxima. So here you have all the wavelength all add up together, which will give you back your white color. There, I draw a rainbow for you already. Okay, this one is 2 marks. One comes from the idea that they all travel the same path at 0 order. So they all add up together for resultant displacement. All the wavelengths and all their paths all add up together. Okay, each wavelength take the constructive, so they all add together. Okay lah. And then the B comes here. They say, describe how you can explain the difference in position of red and blue light in the first order spectrum. So yes, your red and blue light will spread out differently because they have different wavelength. So, for example, if I want to look at red light compared to blue light, okay, your red light would have something like this. Sorry, blue light, red light. Red light will diffract a lot. Blue light will diffract maybe lesser because wavelength smaller. So if this is your first order spectrum, it is also your first order spectrum. So this is your blue light that is reflecting less. This angle is smaller. This angle is bigger. All for the first order. Why is that so? Well, you can think of it this way. The wavelength of red light is bigger than the wavelength of blue light, ma. So it will diffract more. Diffract more. This fella. Blue will diffract less. Why leh? Because if you look at your equation, d sine theta equals to n lambda. Everything else is constant. If your wavelength is longer, means your angle somehow has to be bigger. Okay, longer wavelength, larger diffraction angle. Okay, so therefore you can say your angle of diffraction for red is also bigger than angle of diffraction for blue. For any order lah, for n equals to whatever order. First order you compare, first order. Second order compare. Okay, so we need to describe this. How are we going to describe this thing? You can say your red and blue light has different wavelength. Use the whole sentence lah if you can. Okay, so because of different wavelength, so their position of your first order, which is maxima, where your path difference is lambda. Okay, first order path difference is lambda. Remember, why is it 1 lambda? Go and check your condition of interference. I'm going to shortcut and just say where your path difference is 1 lambda. Because first order 1 lambda, second order 2 lambda. Okay, so because they are different wavelength, so their path difference 1 lambda can be different values. It's different for red and blue light. Okay, because red color 1 lambda may be different than the green color, blue color's 1 lambda. Okay, so blue color, your 1 lambda may be 1 times, what is the wavelength of blue? 400 plus, let's say 480 nanometer. Then you go to your red color, the path difference they need for constructive interference will be 1 times, let's say 630 lah, nanometer. Different already, your value will be different. You need a different path difference. So therefore they will spread out differently lah. So your 2 marks, 1 come here is different lambda, the idea of that. And because of different lambda, you need a different path difference. So this idea lah, different position of maxima. So just remember, that's why when you shine a white light, you will see rainbow come out because all the wavelengths spread at different angle. Okay. Do we continue? Yes, we do continue. Okay, let's do this. So now you know they spread out. They ask you to calculate. The light of wavelength produce a second order maximum at an angle of 61 degrees to the incident direction. So means if you have some light that theta at 61 degrees and you spread out second order of one of the wavelengths. So here you have a light or wavelength producing second order maximum at angle. So you have n lambda equals to d sine theta. If you want to picture, draw lah. Light come in, spread out, second order is an angle of 61 degrees. Okay. So second order wavelength 625 nanometers equals to d. I don't know what's the d, so put there d sine 61. So if you calculate everything, you should get a d value of 1.429. I'm just writing more decimals here. Times 10 negative 6 meter. But they want lines per meter. See, this is meter negative 1. This is just meter. So to find lines per meter, you could call it your n, I guess. That'll be 1 over d. So you're doing the reverse of what you usually do for MCQs. So 1 over 1.429 times 10 to the negative 6 meter. You get meter inverse. So you're going to get something like 6.997 times 10 to the 5 lines per meter. If I round it off to 2SF or 3SF, I get 7.00 or the 7.0 lah, 10 to the 5. Okay, 2 marks. 1 from your diffraction equation, 1 from your final answer. Then you come to another part. Calculate the wavelength of another part of the visible spectrum that gives a maximum for a different order at the same angle. Wow. So you want another wavelength in the visible spectrum. So what's the visible spectrum? You need to know roughly it's 380 to roughly 740 nm. Our eyes can see. that give a maximum for different order. Also, it cannot be n equals 2. Because here we already look n equals 2 ma. So another light will have the same angle as this one in the first part, but it will be different wavelength. So how do we know what is this other light? Yeah, just now we say ma, blue and red and all these all different angle one. So how you can calculate that? We don't panic, we write down our mother equation first. D sine theta equals to n lambda. We're trying to find the wavelength, right? So reorganize. Lambda equals to d sine theta over n. Now, what is our lambda? Okay, you look here, d is fixed. We have the same grating. N is changing, you could say. Theta will also change because of that. So what to do with so many unknown? We just try now. So we'll just try all the n's because it's either 1, 2, 3, or 4, or 5. So let's do that. So if I say, let me try when n equals to 1, then what's your wavelength? So your wavelength will be, what's your D? The D you found previously already lah. Ne? D, use this D. Okay, I'm not going to write the whole thing out because it's a bit long. But D sine of 61. How we know 61? Because of this. They say same angle. So this other wavelength has the same angle as your previous one. So this will be 61 degrees. But another wavelength. So how to find it? So we do though. N equals 1, this one is 1. What do we get? You will get 1250 nanometer. I put nanometer because this is in nanometer. Okay, let's just go a few more. See if we can find some suitable candidates for our n, lambda. N equals 2. Actually, they say don't use n equals 2 like. But if you calculate d sine 61 over 2, you will get back your good old 625 nanometer. That is the same as this one. Where is it? 625 nanometer, the first question. But this one, they say another order. Okay, so let's not use n equals 2. So, we can't use that. Let's try n equals 3. D sine 61, do the same calculation, divide by 3 now. Okay, D sine 61 is a constant. This one will give you 417 nanometers. Let's go one more just in case. Lambda equals to D sine 61 over 4. This will give you 312 nanometers. Okay, I'm going to stop there. You can keep going, but how do you know when to stop? You can have so many order. Right? But you only want the light in your visible spectrum. So, visible spectrum can either be 380 to 740 only. So if you look at your range, oh my, this is out of range. So cannot be that one already lor. 625 is the old one. Okay, your old order, n equals 2. So we don't want that. Wow, what just happened? Now we don't want that. So cannot also. Cannot be. 417, is it within range of visible spectrum? 3804740, yes or? So okay, maybe. 312, a little too short. So maybe in ultraviolet range already. So this one also out of range. So the best candidate will be this one. So it's telling us that this is what color? Blue color light. If we draw the diffraction grating, this blue color light is the third order with an angle of 61 degrees. It will be the same as the previous one, 625, probably orange. I'm just going to draw red. Actually, I can draw orange. Never mind lah. Okay, it will be the same overlap as this n equals to 2 of the red color. They will be the same angle. Okay, so I draw here again, same angle, 61 degrees. That's what it means. You're just trying to look for something that has the same angle but different order. Okay, so that's how you can think of this question. 2 marks for this one. So that means 1 comes from your equation. Do you know how to use the d sine theta n lambda? That one's correct. And then if you have written 417 as your final answer, then that's correct. If you do 2SF, then it's 420. Both correct. Mark scheme you see will write 420. Usually they do 2SF, but you can write 3SF. So A1. 2 marks for this. Let's go. Okay. A few more questions. Almost there. Page 45 is another one. A lot of describing. Okay, this one, you should try it out. It's very similar to the one we just did. Describe pretty much the same thing. So I'm going to skip a few parts. First one, describe the diffraction of light at the grating. Same thing now. You describe wave, go here, spread out into geometric shadow. Just go back to the old one and check it out. By reference to interference, explain the zero order maximum. Hey, this is the same exact question. These three parts are the same. Wow, means very popular. Oh, they like to ask this, so you better know how to describe. Okay, you want to say zero order maximum. The light come in, all the same path difference, so all the lambda is the same. All the colors of the rainbow. So you want to describe the same way. Wave from each slit, overlap or superpose with same path difference, or you can say same phase difference. Okay, and because of that, so you can say they are all constructive in the middle. Constructive or maxima at your zero order. Okay, this one is only 1 mark lah, so it's a shorter one version of the previous question. First order maximum, how would you describe that? Same thing, except that now you're looking at first order maximum, so your colors would spread out differently. Your blue won't spread out as much, your red will spread out more. So you can say now your wave overlap with a path difference AD. With path difference of lambda, okay, 1 lambda, or you can say a phase difference of 360 lah. Okay, so for any zero order, their path difference is 0. Oh, this is 2 marks. I forgot to say. This one, waves overlap, superpose. So N0 is lambda difference or phase difference 0. Then if you go to the first order, N equals to 1, that means you have a path difference of 1 lambda and also a phase difference of 360 degrees, which is 1 lambda. Okay, these are your conditions for interference, guys. Must remember this. This one, B1. Then you come to this part, which is the main reason why we chose this question in the first place. Got graph, you know. This is what you can do in lab. So you will need to use some lab skills here. So you have a diffraction grating, different wavelengths of light. The angle is measured. So this is your dependent variable. You change the light wavelength, independent, and then your angle will change or vary in response, which is why you see here they plot a graph. Lambda is on the x-axis, your independent, what you change. Theta is what you measure. That's on the results, or what your results are on the y-axis. Okay, so if we go down, determine the gradient of the line. Very nice gradient, you all know how to find. Choose 2 points somewhere on your line that you like. For me, if I look at this, I think I like this point. You check the mark scheme, they will choose a different point. That's okay. I like the corner point, and I think I will choose, I like this one also. Cross very nicely in the corners of boxes. It's just easier to read lah. Okay, you get more accurate reading. So here you need to do, what is this point here? 500 nanometer and 0.4. No unit, sine theta is just a ratio. This one will be 300, wow, my eyes, 375 nanometer and 0.30. So these are your points that you're going to use to find your gradient. Gradient triangle, you should do this in lab many times, you should know how to do already. So gradient is delta y, delta x. Also we call gradient m, by the way. By now, okay, this will be delta sine theta over delta lambda, because that's our x-axis. So sine theta will be my values that I chose. You can choose another one, it's up to you. Okay, 500 minus 375 nanometer. So I should probably change this to meters too. Okay, so what's my gradient? I calculate everything. I should get 8.0 times 10 to the 5 meter inverse. So right here, 8 times 10 to the 5 meter inverse. This is my gradient. Now, second part. Whoa, use your gradient to calculate the slit separation D. Now, you must use your gradient here. This is like paper 3. Okay, you find a gradient, use a gradient to calculate something in an equation. But what is the equation though? Check back at this. We are plotting our y as sine and our x-axis is lambda. So you need to rearrange your diffraction equation. N lambda equals to d sine theta. Can we rearrange this into a form of a straight line y equals mx? Okay, so our y is sine theta, so I put that on one side. Y equals to, okay, our x-axis is lambda, so I'm going to put lambda here. Everything else will be n over d. Okay, you see a pattern? This is our y. This is our m. This is our x. So y equals mx. Straight line graph. So if you plot the graph of sine theta against lambda, you will get the graph of a bird, a straight line. Very nice. Beautiful skills you need to use. So this is where you apply your paper 3 skills. So you use the gradient to determine. You already know your gradient is, what is the gradient? Your gradient is n over d, which is this part, equals to the value you found earlier, times 10 to the power of 5. So we need to calculate what is d. This is first order or second order. We need to know n. They got say, check back. Yes, the angle of the second order is measured. So all this angle is for n equals 2. Okay, good to know. So you need to do your second order n equals 2. So everything is 2 over d equals to 8 times 10 to the 5, which means your d will be 2.5 times 10 to the negative 6 meters. That's a spacing between each, this gap the spacing between for your slits. Okay, so you write here 2.5, 10, negative 6. 2 marks. One is if you know how to find your equation, this one you rearrange. Okay, you know how to do this. Equal to gradient. That's a C1 mark and then A1 mark. So very useful paper 3 skills. They will ask you in paper 2 one. Now the last one. On figure 5.1, sketch a line to show the results if you're using your first order maxima. Okay, so all this angle we measure and plot graph is for second order. If you want to use first order, your angles is probably going to be smaller. So I'll just make a note here. First order, your angle is probably smaller for every single wavelength. Okay, and if you're wondering why is that, that's because of our equation. Okay, n lambda equals to d sine theta. If you're using a smaller order, so at first you're using 2, now you're using 1. Okay, so that's decreasing. That is related to your sine theta. So n is proportional to sine theta. Okay, but if you want to see how the line changes, okay, n decrease, sine theta decrease, you need to think of your gradient. What was the gradient again? N over d. Oh, let's rearrange it a bit. So n over d, yes, you put the lambda here, equals to d sine theta. So your gradient, this is your gradient. Gradient is proportional to n over d. So you can say n d is not changing. Gradient is also proportional to sine theta, but I'm just going to look at this. So our n is decreasing from 2 to 1. So your gradient also is going to decrease by half. Okay, so if you are half this one also become half. Makes sense, right? So you can sketch, here they say sketch. So if you roughly draw a line that is a less steep than this first line, then you are correct already, first mark. Now this part, the marks team will say, if you draw a reasonably good line, then okay already. But what is a reasonably good line? If the examiner is strict, then they will see whether it's acceptable or not. So maybe it's good to also take some points, calculate your gradient. Okay, so if I were to do that, I will get roughly from here to this point. I didn't show the calculation, but my new line will be something like this. It's curved. Lines! Oh my word. Let's try this shape thing if I can do that. To here. Why the side here cannot line up one? Okay, I get the idea. Like, it's less steep, but also your origin is somewhere outside there. We don't know where's the origin. So you take some points, you calculate, make sure your gradient, the ratio of change in y over change in x is half. Okay, half the gradient. Okay, so where is my gradient? Down here. Okay, so your new gradient was going to be half of the original of this part. Okay, so that is how you can do your thing. They see you draw gradient less steep, then you say, yeah, okay, they'll give you 1 mark. Now let's continue. The last few questions, 3 more before we call it a day of examples. This one is a very common question. Page 22. A parallel light beam incident on a diffraction grating. Grating has 300 lines per mm. What is the total number of maxima from the grating? So you need to think about this. When you are shining a light through a grating, what is the largest angle that you can possibly have? Largest diffraction angle, this theta. How big can theta go? You think about it, the biggest possible it can go is less than 90 degrees. Because this one is like a bit weird already lah. So it has your angle, whatever it is, that's the condition. Your theta has to be less than 90 degrees. That's the maximum you can go. So how many maxima can you fit inside here before you go to 90 degrees? That's the question. So you look at your equation, and lambda equals to d sine theta. We know that somehow we have to be less than 90 degrees. Okay, whatever your n number is. So we need to find what's our maximum n number lah. So sine theta is, sine 90 is 1. So you just n equals to d over lambda. So you have n equals to, what's our d? 300 lines per millimeter. So we need to find d. 1 millimeter chopped up into 300 parts. So that will be, what's my value? I haven't found my d. Whatever the d is lah. Okay, you can use this in your further calculation. And lambda is 600 nanometer. So 600 times 10, negative 9. If you do d divided by lambda, you will get 5.55555555555. So the next thing you remember is n is an integer. Okay, integer, a whole number, n equals to 1 and 2, 3. So you cannot have 5.555. So the nearest next integer smaller than this value will be 5. It cannot be 6, although you say it means can round off. No, 6 is larger than this 5.555. You want something that is less than, so 5. So what that means is, if you draw a picture of the grating, you can go 1, 2, 3, 4, 5. Wow, that's a lot of order maxima. N equals 1, n equals 2, n equals 3, n equals 4, n equals 5. Don't forget n equals 0. So there's 5 on 1, 5 there, and then 1, 2, 3, 4, 5. In total, how many intensity maxima? So you have 5 on one side, 5 on the other side, and 1 in the middle. This is our 0 order. So in total, you have 11 maxima in your grating that will split up. So if you put a light through there, you will see 11 lights come out. If you put a face there, you'll see 11 faces come out, because all the rays will all split up and spread out. Okay, it's a very good skill to use. Key idea is sine theta must be less than 1, or theta must be less than 90. Okay, almost there. Next one's on page 18. Monochromatic light is incident on the diffraction grating. First order maximum observed at an angle to the incident. Wow, this one look easy, but got small trick question. They give you lambda, very nice. They give us the first order angle. But then now they ask you the angle between the first and second order. So they're asking for what is the change in lambda between your second order and first order. So you need to find both. Yeah, find both. There are many ways to do this. I'm just going to show the more straightforward way. Number 1, okay, you want to use your n lambda equals to d sine theta. So first order, what's the wavelength? 5.3 times 10, negative 7, equals to, what's the diffraction grating? They didn't give us never mind, put d first. And then your angle, sine 15.4. Okay, so then you can find a diffraction grating value, which will help you in your second case. So diffraction grating, you should get about 2 times 10, negative 6m. Okay, Okay, then you do your second case. The second order. So what will be the second order angle? Second order will be 2 lambda, same light, so same wavelength, equals to, oh, now we know D. So D is 2 times 10, negative 6, but we don't know the angle. So we go sine theta, theta 2, I should say. So now you need to find your theta. You remember how to do trigo. Make sure your calculator is in degree or radians mode. Degree lah, because the answers are in degree. So you make sure you calculate theta properly. You should get 32 degrees for your second order angle. Okay, so your light go split first order, second order. Maxima lah. So this one is, what is the angle? 15.4. This one is 32. 15.4. So they're asking the difference between the angle, which is then this red color one. Okay, so we need to do delta theta will be 32 degrees minus 15.4. 32.0 lah. That should give you about 15.4, 16.6, somewhere there. I rounded off a bit already. So the closest to that will be the answer C. So make sure you know to find the answer C. Okay, just remember lah, this is a trick question lah. They say angle between the first and second order, so you need to think of this. That's just a new thing. And the final question for the day, it's about rainbow again. All the rainbow light split out. Oh, let's look at the question. Page 17. White light got wavelength. Wavelength of red is approximately twice the wavelength of violet. So let's make that a fact. Wavelength of red is roughly 2 times of violet. So when white light shine in spectra can be found, which one show the correct spread of your order? So you need to think, your red light longer wavelength, right? So your R will diffract more. Why? Because n lambda equals to d sine theta. D sine theta. If your thing is longer, so your angle will be larger. So your angle, let's write a new line. So angle of red will be bigger than the angle of violet. Okay, so it will spread out even more. So if you look at your choices, this one, look at A. V is spread out more than R, cannot be. Wrong there. This one also, V is spread out more than R, so cannot be. So left C and D. So if you not enough time, you just tembak, you just simply choose one. You have 50% chance to get it correct. But we need to know, we want to know, is it RV or RV? Are they equally spread or are these angles changing? So you need to think about this thing again. N lambda equals d sine theta. So as you increase your order, your theta will increase as well. Right? N equals 1, N equals 2 is bigger, things like that. So if your angle, your n number is 2 times bigger, let me just rewrite this. N is 2 times bigger, means this also has to be 2 times bigger. And as you get bigger and bigger, because of your sine graph, like what I mentioned, okay, your sine graph is a curve. So if you're going from, let's say, here to here, 2 times, your sine theta is 2 times, your angle will be a little bit bigger. Okay, here increase 2 times, and this is because of n equals 1, n equals 2. Then here your theta 1, theta 2. The gaps between that will be bigger. So here got one gap, here got another gap. So as you go further out, it should be more spread out lah. So not D lah. D is like here and here. This is your delta theta, by the way. Your delta theta is roughly the same, so it doesn't look quite right. So the delta theta should be bigger. So like this one, first order, a bit small. Second order, much bigger. Okay. Then this one, first order, a bit small. The second order, much bigger. So this is C lah. Okay. If you want to think of it another way, you can also see, okay, I don't care about violet or red. I just want to look at violet. So violet is here. This is the first angle for first order. Second order, 2 times bigger. Correct? Okay, that's another way to think about it. Red, you can also think of the same way. First, second, was the same. So yeah, this one is not quite right. Look at that. Also, if you want to check, they are overlapping here at the first order. So that's just a fun fact. Right, so think about this one, the angles and overlapping. That is all for today's examples, I think. There's only a few more pictures to see. If you find it hard to imagine the white light, just think of this now, spreading out. Okay, you see this one has the largest wavelength, spread out the most. This one has the smallest wavelength, spread out the least. But if you want to think of the order of second order, third order, then you have to go back to the picture that we saw in the theory lecture video, which is this one. Okay, so your first order here, you see they're kind of pretty close. But then as you go to second order, wow, they all really spread out at really, really different angles already. So that is what we're looking at now. The higher order you go, your whole spectrum will just get bigger and bigger, more and more spread out. So this graph or this picture is what you are seeing in these choices. Okay, as you go out, your rainbow will be more and more spread out. Okay, so yeah, this is the idea of it. So that's all for this chapter. Go try out more questions if you feel like, I want to try some more practice questions. Yes, please do so. That's all for this one. See you in the next